Oh, you're better.
Okay, welcome. Let's try to start on time. So today it's my great pleasure to introduce Subir Sachdev, Herschel Smith Professor of Physics at Harvard University. Professor Sachdev did his undergraduate study at MIT and then his PhD from Harvard. Then after many years of positions at Bell Lab and on the faculty of Yale University, he returned to Harvard at 2005. So Professor Sachdev has made a lot of seminal contributions in various fields of condensed matter physics, such as in magnetism, unconventional superconductivity, quantum criticality, non-Fermi liquid, among many others. And his work on strongly correlated electron systems have provided key insights into the strange metal and pseudogap regimes of the cuprates, which some of which I believe will be discussed during the talk. And beyond just condensed matter physics, his ideas have had a significant impact in high energy physics as well. He co-developed what is now known as Sachdev-Kitaev model, or SYK model, which is an exactly solvable, strongly correlated quantum matter model, which has become central for the ongoing discussions on chaos and holographic duality. And besides research, his books, Quantum Phase Transitions, and most recently, Quantum Phases of Matter, has become standard references for this topic and have influenced generations of physicists. Okay, so Professor Sachdev has received many major honors. To list a few, they include the Lars-Onsager Prize, the Dirac Medal, and he's also a member of the National Academy of Sciences and a fellow of the Royal Society. Finally, on a personal note, it's a particular honor for me to introduce him today, as he was my postdoc mentor. I benefited a lot from various discussions with him. Okay, so please join me in welcoming Professor Subir Sachdev.
Thank you very much, Jushi. It's a real pleasure to be here in Atlanta, especially on a beautiful, almost spring day. And thank you for that very kind introduction. It's very nice. All right, so my talk here is, as advertised, mostly about the high-temperature superconductors. But as Yushi mentioned, there have been connections on work that was initially done solely as a condensed matter physicist, studying high-temperature superconductivity. That has led to connections with issues in black hole physics, which I will mention briefly towards the end of my talk. And the common thread in everything, as you'll see, is really many particles, in particular, many-fermion quantum entanglement. So that's a relatively new topic in physics, which before 1980 was really not even a subject, but now has become quite central to many fields of physics. All right, so what are the high-temperature superconductors? The ones I'm talking about are these cuprate materials, which were discovered in 1986. So they have a critical temperature of around 100 Kelvin or a bit lower. So that may seem very cold, but it's above the boiling point of liquid nitrogen, and liquid nitrogen is very cheap, so that's really not a problem for potential applications. There have been other higher temperature superconductors discovered since then, but they're all at extremely high pressures, and you can only make very tiny samples. Here you can hold it in your hand. It's a ceramic material. You can make large amounts of it, and all you have to do is to dip this in liquid nitrogen, and it's a superconductor. So you can do an experiment like this, where you have dipped that cake in liquid nitrogen, and now it's floating above a track of magnets. Of course, at this point, it's warmed up, and so it crashes down. And this is an experiment you can do in a little classroom. And it's still the only material where you could do this kind of experiment. You don't need a big refrigerator or anything like that. So people, of course, have been hoping there'll be very many applications of these materials. And there have been quite a few, nothing major. But here's the potentially a killer app, where this is a magnet made of IBCO, that's IBCO wire, which is being used to confine a plasma of neutrons and protons and others, and in the hope of producing plasma fusion and then energy. And there's many companies around the world that are now doing this. This is from the website of a company in the Boston area. And let's see if this works, but it's really very exciting where the ability of these materials to produce high magnetic fields over a large volume is the key for this potential application. All right, I won't be talking about any of the applications. My interest for longer than I care to admit has been really the microscopic physics of this material. So the crystal structure looks quite complicated with several elements. But fortunately, for the purposes of this talk, we can focus mostly on just the orange dots. These are the copper atoms, and they form a simple square lattice. So we just take a square lattice of these copper atoms, and in particular, there's only one orbital on each copper site. So just think of each copper site as an electronic state that can have 0, 1, or 2 electrons on it, and nothing more because of the exclusion principle. Now, at a certain density where these materials are insulators, you in fact have exactly 1 electron per copper site. And then they form this antiferromagnetic arrangement. And this is due to an exchange interaction between the spins, which is positive in sign and makes the spin polarized in this checkerboard arrangement. So this is an insulator because if you try to move any of the electrons, you will be forced to create 0 and 2, for example, if this moved to that site. And that would cost you a lot of repulsive energy, and so that doesn't happen. All right, so this is extremely well understood today, the properties of this antiferromagnet and its excitations. All right, so our key idea in the field, which has been debated a lot and still hasn't found complete fruition, I would say, but I think really something that set the right direction and we have to think about was a very important paper by Phil Anderson in 1987. And he said that the key to high temperature superconductivity is the formation of what he called a resonating valence bond state. We barely knew what that meant, in 1987. Today we have a much better idea of what this state means. So this is how he described it. Imagine, just had 2 spins. And then these spins on their own like to form a spin singlet. It's like a valence bond where you have spin up, down, entangled in this manner. So now, but you've got a whole lattice of these spins. And each spin can only pick a single partner to form this valence bond. And so when you partner them up, you get some dimer covering of the square lattice. And his bold suggestion was that the kind of state we need to think about, rather than this antiferromagnet, is a quantum superposition of all different ways of covering the lattice with dimer configurations. So there's an exponentially large number of such configurations. And these are all superposed coherently in some manner to give you some approximation to what this resonating valence bond state. All right, so this state really was a very new type of state in physics. We barely understood what it meant. But one way to say it is that this is a state with long-range quantum entanglement. It's got entanglement not just between nearest neighbors, but entanglement between all the spins together, because all these different dimer configurations are coherently superposed in a state like this. All right, and this type of state is what today we would call a quantum spin liquid. And much is known about quantum spin liquids today. We have a classification. You can look up what are the different possibilities and what are their properties. But there's one weakness to this theory of quantum entanglement. It's really a theory of entanglement of bosons, because what's happening among the different dimer configurations is that the spin is rearranging in some way between the different dimer configurations, but no charge is actually moving. The charge of each electron is stationary on each site. So in fact, it's just the flip spin that's moving around, and those are just bosons. So the Fermi statistics of the fermions is playing no role in this entanglement. Okay, so now let's, one more thing. So what is the effect of this entanglement? And I could say, well, it's described by topological field theory and so on, and give you a lot of fancy words. But really, it all comes down to one very basic property. And the basic property is that its excitations cannot be created by local operators. So for example, if you took the singlet bonds and broke it apart into individual spins, this is not really the right excitation for the system. What can happen because of the entanglement is that one half of the pair can move away to infinity. And so now you're left with this single unpaired spin moving around. And that is the true excitation, which we call a spin-on. And it has a property that as this moves around, it's carrying spin but no charge. And this is a whole new type of particle in physics. There's nothing you'll find in the textbooks before 1980 that would talk about such a fractionalized excitations. We call it an ennion because it have all kinds of strange properties due to the entanglement. But you notice to create a spin-on, you needed to move the other one to infinity. So that was not a local operator. And the correct language to talk about such spin-ons is in terms of emergent gauge theories, which I won't say much more about, but hopefully it's just clear from this very simple picture what's going on. You can think of this as carrying some emergent gauge charge, and the thing that moved the particle all the way to infinity was some electric field and some emergent gauge charge. But locally, you really have to move the other one away to create the right excitation. Okay, so that's the new idea that now has played a fundamental role in many, many things in condensed matter physics and also other fields of physics. Ideas on quantum error correction are also closely connected to these. Okay, but moving on. So how do I get a superconductor? Well, what I have to do is to start from that insulator and remove a fraction p of the electrons. So that's what we call the hole doping p. And eventually, for hole doping around 15%, you get your high temperature superconductor. Okay, so that's really what we want to understand, and still a function of some debate today on exactly what's going on, much debate, in fact, near the onset of superconductivity. So now if you remove a few holes, now you see that the electrons can move around, so it can become a conductor, and in fact, become a superconductor even. And once these electrons are moving around, then you have to worry about their Fermi statistics. And one of the reasons I think we still don't have a complete understanding of this phase diagram is that the multi-fermion entanglement is a lot more complicated than multi-boson entanglement. There's much less work on multi-fermion entanglement, but that will be the focus of my talk on some simple models of fermion entanglement and how they relate to observations in these materials. But okay, that's really for the next 40 years, I suppose. But I think we're making a lot of progress. All right, so, but let me talk about some simple things that are well understood. So I said that the density of these vacancies or holes was P. But if you were a semiconductor physicist, that's not how you think about counting holes or electrons. You count them relative to a filled band or an empty band. So in this case, if I want to fill every state available to me, I can put 2 electrons on each side. So relative to the state with 2 electrons on each side, the density of holes is 1 plus P. That's what you would do if you were a semiconductor physicist, or if you ignored the interaction between the electrons. You do some band theory and say there's a filled band that has 2 electrons per side. So the density of holes is really 1 plus P. And similarly, if you're doping electrons, then you would say the density of electrons, I can just see them, relative to the empty band is 1 minus P. That's how many electrons I have per unit site. Okay, so which is it? Will I see 1 plus P holes if I ignore the interactions, or will I see 1 minus P electrons? Now, how do you measure the density of electrons in a solid state material? The way it was originally measured by the Hall effect. You apply a magnetic field and you measure the resistance in the transverse direction, and it gives you the density. That's how we first knew that electrons, charge is carried by electrons in materials and not negatively charged carriers. Okay, so you measure the Hall effect and you get some rather complicated results, but one place where you get a very nice and well understood result is out here, this so-called Fermi liquid regime, where you do indeed see 1 plus P holes. Okay, great. So why am I seeing 1 plus p rather than 1 minus p? That has to do with certain details of the band structure. So you can measure what's called the Fermi surface by photoemission experiments. That tells you the boundary between the occupied states and empty states. So this is now momentum space. Momentum going from 0 to 2 pi over the lattice spacing. So these are all different states available to free electrons in momentum space. And it turns out that the occupied states are here and the empty states are here. So now you look at the empty states, when you extend the Brillouin zone periodically, that's just a simple circle. So because of this very simple shape of the whole Fermi surface, just a circular shape, it's a much better approximation to think of it as almost free holes. It's not such a good approximation to think of it as 1 minus p electrons. And so that's really why, and with this well understood, you get this Hall coefficient of 1 plus p. All right, so continuing with well understood things, there's a very deep theorem of condensed matter physics, which was discovered in 1960 by Luttinger. And today we know that actually it's a piece of topological physics that appeared long before its time, and a brilliant paper by Luttinger, but really hard to understand. What he showed was that suppose I have some free electrons with this Fermi surface, then I add in interactions between the electrons. Interactions are absolutely crucial for everything in the phase diagram, so add them in. So what Luttinger showed was the interactions can change the shape. All the shape can change and so on, but they cannot change the area enclosed. So there's a topological invariant in a strongly interacting many-body system. And the shape of this boundary between occupied and empty states can change, but the area enclosed cannot. So that's called the Luttinger theorem. And he proved it to all orders in the interaction, which is not the same thing as exact, because there could be some non-perturbative effects that give you other states of matter that are not connected to the free particle state. And that also worked beautifully. You do the experiments, you know the value of P from chemical means. You measure this area by photoemission, and it works. All right, so things are looking up, at least over this regime, but that's not the most interesting regime because the TC is rather lower down here. Okay, so let's go to the other opposite limit, which will be the focus of much of my talk. That's called the pseudo-gap metal. And here you find a surprise. You get a Hall coefficient of holes of density P over a wide regime here. Now, in the antiferromagnet, I showed you the picture. If you actually had an antiferromagnet, then again, that's easy to understand because the density of holes in the antiferromagnet was P. But here the problem is the antiferromagnetism disappears. So you're in the most interesting regime where there's no antiferromagnetism, where you get a Hall coefficient of density P. So that's been, I would say, one of the central problems that we've been arguing about for 30 years now, as to how do you understand this state with density P carriers and no apparent order, or like in the antiferromagnet. Now, there have been many theories of so-called intertwined orders with all the different orders you see at low temperatures, antiferromagnetism, charge density waves, superconductivity, and so on. I won't go into this. And this theory has many success. The idea is that, yeah, these orders are all there and they're fluctuating, and that can explain some of the experimental properties. Okay, all right, so that's been progress. So what I'm going to talk about, the central part of my talk will be that's not a complete picture. And we'll talk about some very recent experiments that support a picture we've been working on for a few years, which is that really there's a new type of quantum state, a metallic state, which because of quantum effects and not because of some thermally fluctuating broken symmetry, has the right properties to explain the pseudogap. And you don't really have to worry about these intertwined orders, at least initially. And really to develop a theory of this kind of state, you really have to understand quantum entanglement, not of bosons, as in spin liquids, but of fermions, mobile fermions. Okay, so So I'm going to talk about two different types of states to explain aspects of the phase diagram. The first part, I'll talk about this pseudo-gap regime that I just mentioned. And then I'm going to talk about a state that we somewhat unimaginatively call fractionalized Fermi liquid. And you can think of this as almost like a superposition of two different quantum states. There's a quantum spin liquid, which has the spin-on excitations, and there's a Fermi surface. And so it has excitations both of Anderson's quantum spin liquid and also of Luttinger's Fermi surface. And exactly how that superposition occurs and how that leads to experimental observables, that's what we've been thinking about a lot. Then in the second part of my talk, or last third, I would say, I'll say a few words about the strange metal, where this already mentioned SYK type model plays a role. And this is another example of a state which has mobile fermions. But unlike the pseudogap, where you still had some fractionalized excitations, spin-ons and quasi-particles and so on, here, in fact, it's a state with essentially no particle-like excitations. So complete breakdown of the particle concept, again, due to strong quantum entanglement. And so it turns out that this type of state we initially came up with in '92. Ye was my first graduate student. In thinking about exactly these issues associated with the phase diagram, but it's turned out since then that this model is in fact just the ticket to understand certain properties of black holes in our space-time. And I'll say a little bit about that also, if I time things correctly. And finally, in the last few minutes, I'll talk a bit about the transition from the FL star to the FL using the SYK model, which I think is starting to give us some insight into the original model that motivated all this, the original physical problem, which is the strange metal. Okay, so that's the many things I'm going to cover, but let me first talk about the issues having to do with this pseudo-gap regime, where you have charge transport without any apparent broken symmetry of holes of density P. Okay. So how can such a thing even happen? So this is, of course, the famous theorem that I told you about of Luttinger, that if you have a system of pre-holes, let's say, of density rho, then which I've been calling 1 plus P also, but in terms of rho, the area enclosed by the Fermi surface is just rho over 2. The 2 is the factor of 2 for spin. And this is in units where the area of the Brillouin zone is 1. Okay. And okay, so an important development which really signified the topological character of Luttinger's theorem was a beautiful paper by Oshikawa at the turn of the century, where he re-derived the Luttinger result in much simpler arguments, using what now sometimes is called an anomaly. So again, I won't go into it, but the paper is readable by all the students in the audience. It simply looks at what happens when you put the system on a torus and what happens when you insert one flux quantum through the whole of the torus, and just computing that in two different ways gives you the constraint on the area, which is exactly Luttinger's area. Okay. All right, so soon after Oshikawa's paper, we said, okay, this allows you to get around the Luttinger constraint. So again, consider the same system, very generally, of density rho. And Luttinger said that the area must be rho over 2. Well, what we pointed out was you could subtract 1. The area of whatever the Fermi surfaces are, and why I'm drawing this strange shape, I'll explain a bit later, can be rho minus 1. So you can get Hall coefficient of carrier density rho minus 1, which is, of course, P, which is what you see. And then there should be a Fermi surface, of course, the corresponding area. And so how could this possibly happen? Well, the only way this can happen is if non-perturbatively there's an entangled state around. And that entangled state can take up the deficit in the Yoshikawa argument, the momentum gain when you insert a flux through the whole of the torus. So it turns out that exactly one can be eaten up by some spin liquid of the resonating valence bond variety. And the rest will be exactly that due to the Fermi surface, just as computed by Luttinger. And there's no broken symmetry. All right, so important to say about it is, first of all, this deficit of one is quantized. You can't just subtract any density. You can only just subtract certain rational amounts, and one is the most common. You could subtract two anyway by putting a fill band. So subtracting two is not a problem. Luttinger did that. But subtracting one, an odd number, is a new thing. And then, so in fact, and if you subtract one, this is essentially one of the most striking consequences of long-range quantum entanglement. I told you they have this entanglement, but it's really hard to measure. People are coming up with different ways of characterizing the entanglement. This is one of the easiest experimentally. Just measure the area enclosed by the Fermi surface. All right. So let me give you now, construct an actual wave function. Let me wave my hands a bit and actually construct a wave function for this new type of metal, which is partly a spin liquid and partly an ordinary Luttinger Fermi liquid. Okay, so let's start with the antiferromagnet. It has a broken symmetry of spin up and spin down. And so the Brillouin zone, the Fourier space, is this diamond here. States over here and states over there are related by 2 pi wave vector relative to the unit cell, and so they're the same states. So you can now remove a few holes while maintaining the symmetry, the broken symmetry. So now you have exactly p holes moving around, and you can then compute how they move, then very much like in the usual band theory. And you find you get 4 such pockets when you do this computation. Well, not really 4, because I said, states here are the same as the states over there. There's really only 2 pockets, because this pocket is really the same as that. It's just a Fourier, in terms of the lattice. But things on the lattice, it's not a distinct state. So you have 2 pockets, but you have a degeneracy too of spin, because you can these holes when they move around in an antiferromagnet do carry spin. And so the area of each of these pockets is p over 4. Okay. But now so that's still a Luttinger type state. Let's go to something exotic. So this is what Anderson had in mind when he started talking about resonating valence bond states. You take a resonating valence bond state and you remove a few electrons. And now when these vacancies move around through the resonance, what you see that what's moving is charge E but no spin. So this is not really a hole, it's an anion, which exists in this resonating valence bond state, which carries charge but no spin. So it's also a very exotic object. The density of these objects is P, and it carries charge, so it can explain the Hall effect, provided it's a fermion. All right, great. And what kind of, but fermions, Luttinger has told us, and Yoshikawa, it must form a Fermi surface. So what is the area enclosed by the Fermi surface of these holons, as we call them? Well, if you do some computation, again, you get 4 pockets of spinless objects. So now, again, the area is P over 4, because there are 4 pockets but no spin. So it's the same answer as an antiferromagnet, but for very different reasons. And these are objects which carry charge but no spin, the quasi-particles. And this is where, how this works is that you do have this resonating valence bonds, which give you the spin liquid anomaly, and then you have the Fermi surfaces that give you density P, and so, okay. All right, so this is a possible state for the pseudo gap. But one feature of this state that I have to mention here, is that there's no coherent interlayer transport. What this means, if you have 2 layers next to each other, which you do have, then these holons can't go from one layer to the next, because the existence of a holon depends on all the entanglement. The entanglement is only within the layer. There's very weak coupling between the layers. So the holon can't really go away from the spin liquid, only an electron can come out. That means it has to capture a spin from somewhere and then come out. So there's no coherent interlayer transport. And this will be key to the experiment I'm going to show you. All right, so that's the hole on metal. So what is my favorite state? Well, the favorite state is what I call FL star, and how do you form it? So this is how you can think of it. Imagine you break some of the singlet bonds like I did before, and this has created some spin-ons, and each bond costs you energy about a J, the exchange coupling. And now what can happen is that these spin-ons can move around, and each of them can find a hole-on, and the two of them can form a bound state. So that's that green dimer, which is a bound state of a hole-on and a spin-on. And so the green object has charge E and spin a half, and in fact, it's a fermion. So in other words, it's actually just an electron. And the reason this bound state will form, as you can see, because when the hole-on and spin-on are resonating with each other, you're getting an energy of the hopping matrix element T, which is bigger than J. So in the ground state, in fact, the hole-on type state that Anderson and others have talked about for so long is actually unstable. The hole-on and spin-on actually bind each other and form these dimers, the green dimers, but the spin liquid will still be there. So it's not a conventional state, it's a rather exotic state, which has got, if you look at it in a colorblind way, it's just a same old resonating valence bond state, but it's also got these green objects moving around, which are fermions. The others are bosons. So it's this mixed sea of fermions and bosons, and these fermions must form a Fermi surface. So again, they form 4 pockets, but now they're spin a half. So there's 4 pockets and a factor of 2 for spin, so the area should be P/8. Okay. And furthermore, these objects can tunnel from one layer to the next because they have just the right quantum numbers. They have charge E and spin a half. They're just electrons. All right, so why am I going on about all this? You'll see in a minute. So just to summarize, there's the antiferromagnetic ordered state, which is conventional with area P/4. The hole-on metal, which is highly unconventional but has no interlayer tunneling, and there's a FL star. Okay, so these are all, you can just come up with these areas very simply just by looking at these cartoon pictures. But the answer is that this is one feature that's exact. There's no change, there's no corrections to these results. Sort of like the quantization of the integer quantum Hall effect. It's exact. This is kind of similar to that. So that's why, since we can't compute much in this system, let's focus on the things we can compute exactly. And furthermore, these areas can be measured. So that'll be the next part of my, and I just say this P/8 was actually mentioned in a paper by us in 2007. All right, so now let me talk about a recent experiment. I could spend the rest of the semester talking about all the experiments on the cuprate pseudogap. I'm of course being very selective. I'll talk about one experiment, but okay, I'm happy to discuss your favorite experiment later on. Okay, so this is an experiment just published last year by a group at Los Alamos, and they looked at this particular material, this mercury compound, rather than the other materials. And they looked at how it transfers current in this direction, this what's called the C-axis or the Z-axis. And the mercury material is actually the favored material because it has very simple, if you look at the blue sites, which are the copper sites now, they're right on top of each other, blue on top of blue. So it's called what's called AA stacking, whereas the others are more complicated. And that's what makes the experiment possible. So they take this material at doping 0.1 at this temperature, around 80 Kelvin above TC. And the reason they're working at such high temperatures is they want to get rid of all broken symmetries. They don't want charge density waves, superconductivity, or anything. They just want a metal, which is, this is a very interesting metal because it has a high TC. So before we understand TC, we have to understand the metal. Okay, so what did they see? So what they did was they apply a magnetic field at some rather bizarre angle and measured the resistance in this direction. So there's a magnetic field as a function of angle theta with this axis. This is theta here. And then there's phi, which is the in-plane angle. And I won't go into the details, but I'm happy to go to the details. Their data is beautifully fit by a very simple model. The simple model is there are indeed 4 pockets of variable area. And these pockets have a very small tunneling from one layer to the next. That gives you this T-perp and gives you the Fermi surface has the shape of a warped cylinder, 4 warped cylinders. You've got this, in the XY plane, you've got this ellipse. And then if you go in the Z direction, it warps a little bit. That warp comes from the tunneling from one layer to the next, okay? Anyway, so they measure as a function of theta and phi, the different values of theta and phi, just the resistance in the third direction. And I see certain peaks which are very characteristic, theta Yamaji, from which you can read off the area of the Fermi surface. In fact, this is the calculation from a very simple Boltzmann equation compared to the data as a function of theta for different values of phi, and it all works very beautifully. These are their calculations. So from this good agreement between their simple model and the data, I'll just tell you their conclusions. The observation of the Yamaji peak is evidence for a small Fermi surface pockets in the normal state of the pseudo-gap phase. So that's already, the best evidence we have for such a thing so far. I mean, photo emission for various reasons doesn't work very well here. And not only that, they're pockets which give you the warping of the Fermi surface. So there has to be tunneling from one layer to the next. And that pretty much rules out the hole-on metal. The RBB state that in the simplest version that Anderson was working on, and many others, it simply cannot explain this data. Maybe there's antiferromagnetism. Of course, in the real world, we know there is no antiferromagnetism at this doping, but you're applying a huge field. This is 80 Tesla. Maybe that field changes things and there's antiferromagnetism. Okay, but it has to be coherent between layers. And anyway, so we can't rule it out completely. Okay, then going on, the small size of the pockets, each estimated to occupy only 1.3% of the Brillouin zone, is not expected, okay, given the absence of long-range broken translational symmetry. Well, okay, I will say, all right, we did expect it, fine, but most people didn't. But also very interesting is the size. They say the size is 1.3%. And we predicted P over 8, which is 1.25%, 20 years before the experiment. Or not 20, 15, I think. Okay, so very excited. The other possible state is the spin density wave, which would give you P over 4, which is a factor of 2 off. So it's hard to believe that, something's wrong by a factor of 2. So anyway, so this is, I would say, the best evidence is, first of all, it's nice to have in this field a quantitative prediction. And it's really the best evidence for this kind of many-fermion entanglement, because you can't get a Fermi surface like this, of this size, with coherent interlayer tunneling without some many-body entanglement. You need the spin liquid there to get around the constraint placed by Luttinger's key theorem for conventional states. All right, so okay, so I hope this represents some progress. Okay, so, but I said this is really about certain invariants of the Fermi surface. What about, is there any other evidence? Well, there's quite a bit, I think, but I'll focus on one other recent experiment, which is done using ultra cold atoms. So this is really, I would say, one place where quantum simulation is playing a big role in advancing our knowledge of quantum matter. So these are experiments by the group of Emmanuel Bloch and several other groups. They make very large samples of fermionic atoms. And quite remarkably, they're able to image every one of them. In some destructive measurement, they can measure the spin and the charge on every site, something that's unimaginable in condensed matter physics. And so what they measure in this particular paper is what they call a multi-point correlation function. So they take many, thousands of such pictures, and they find where the holes are. So maybe there's a hole there. So that's where the hole is. And then they look at the relative spin of this electron, this site, and that site. And then they average that over many samples and many holes. So they end up getting the two-spin correlation function in the sites around the hole, not everywhere else, but just around the hole. And this is a picture of various two-spin correlators around the hole as a function of density. And they're really working out here in this rather high temperature regime where there is no sign of any charge density wave or superconductivity or anything else. But what they see very clearly that the correlations in the large doping regime are very, very different from those in the small doping regime. Okay, and so that really means there are two different quantum many-body states here. Nothing to do with any broken symmetry. One they call polaronic. So their polaron is exactly what I call a hole-on spin-on bound state. That's the state I would have called FL star, but fine. I'm happy to live with polaronic. And this is Fermi liquid. And so there is at least some qualitative evidence here of, again, something very different between the metal here and the metal there. So after this paper appeared, we took our model of the fractionalized Fermi liquid. So there's a model we call the ancilla layer model, which I don't have time to talk about. It has a one variational parameter, phi, which is actually turns out in some low energy gauge theory to be a Higgs field. And is non-zero. It has a Higgs condensate in FL star, but not in the Fermi liquid. And we computed in this model, I should say these people here, as a function of doping various of these correlation functions compared to experiment. And you see it does reasonably well. Okay. So we're starting to understand a little bit better now the nature of the metal which is underlying this famous pseudo-gap regime. Okay, so that's the first part of my talk where I talked about the pseudo-gap and a particular type of many-fermion entanglement, which, as I said, has both a spin-liquid character and also a Fermi surface character and lots of different types of anionic excitations. Okay, now I'm going to talk about a completely different model, which we're hoping ultimately will describe the strange metal. So let me first describe the model, which is really relatively simple. So imagine you have some sites. Let's put them in random. So there's how many? 19 sites here. And some fraction of them I'm going to occupy with the fermion. I'm ignoring the spin. All right, so now I'm going to let these fermions move around or tunnel between the sites. And now if they do that, eventually they will form a Fermi liquid. We know that the ground state eventually looks very much like Luttinger might have imagined it. So we're going to put some restrictions. And the only restriction we're going to put is that they're allowed to move as fermions only in pairs. So for example, seems as kind of an artificial restriction, but we're just looking for some models which has some strange metal character at this point. That's what we're doing in 1992. We were just desperate. So we said, okay, there's some amplitude that 11 and 12 will tunnel to sites 5 and 14. So every such process has some amplitude, tunneling amplitude, which I call this number U. Okay. So in quantum mechanics, everything that's possible is allowed. So you allow also any pair of sites going to any other pair of sites. And each such tunneling amplitude will have a complex number associated with it. So there's order n to the fourth complex numbers. But remember, there's 2 to the n sites, 2 to the n states here. So the number of complex numbers is much smaller than the number of quantum states. But so I can ask you to ask what is the dynamics, what does the ground state look like, what do the excited states look like? And this is essentially an impossible problem to solve because the number of states is 2 to the n, and that grows very rapidly. You can't even put it on any computer and solve it. So what we pointed out was that it's possible to solve this in a certain limit. we just make one simple assumption. You assume these are independent random numbers, that every such process gives you an independent random number Q, U. And then in the large n limit of having a large system, you can solve the properties. And moreover, the properties are independent of the distribution and of the realization of the numbers. It's basically self-averaging. And so you can solve it. I won't go into the details, but it's once you have the idea to do that, it just takes a few steps to go ahead and solve the properties. And so you get what's now today understood very reliably to be a model of multi-particle quantum entanglement, mobile fermions. And indeed, it yields a metal. Here, by a metal, I mean a compressible state. We can have arbitrary density, whose excitations are not particle-like. That means there are no bosons, fermions, anyons, nothing. So what is the excitation? Well, it's just some entangled quantum soup. That's the best I can say. But you can solve it. You can solve various things. So what is the consequence of this entangled quantum soup? Well, they turn out to be one very beautiful property, which we already understood in 92, 93 was connected to things happening in the experiment, because there were indications of this in the experiment. Imagine you take this system of strongly interacting electrons with no particle-like excitations, and you just perturb it a little bit. You kick it, and then it'll move around, it'll thermalize, it'll reach on its own, it'll reach some long time state. And that state will be described by a temperature. Then you can ask, how long does it take to reach that state? Well, so that's the time tau. Ignore the omega for now. So h bar over t, that's the time, will be in fact just kT. So that's something you can essentially show in these models. And it's quite remarkable, because if you ask that question to anything in your solid state physics books, the way you would solve this problem is write on Boltzmann equation. Take some distribution for Boltzmann equation, and you let it run by Boltzmann equation. And the way things equilibrate in Boltzmann equation is by the collision term. So the rate of equilibration depends on the strength of the collisions. Here, there's only one energy scale, which is the root mean square average value of U. So U is some number. Amazingly, that number doesn't appear anywhere. It's independent of the strength of the interaction, provided your temperature is below the scale U. Of course, if T is very high, then U will appear. But the low temperature limit, the time scale is independent of anything, just Planck's constant, which is why it's called the Planckian time. But this is something you can show. This is the simplest model where you can show this. And so that, of course, got us very excited. But it's been a long route from that to connecting up to real experiments. Here I mentioned a beautiful recent experiment in the group of Peter Armitage and Johns Hopkins, where they see very clearly evidence of this, what they call Planckian dissipation through some nonlinear response. And in particular, they also show that it is not due to coupling to phonons, which gives you some very weak energy relaxation rate, but it shows up in the momentum relaxation rate, meaning that the impurities are actually quite important to understand this in the real system. So that's also good for the SYK model, because that is made up also of some random numbers. Anyway, okay, so how am I doing on time? 5 more minutes, okay. Then I won't get to the theory. Yeah, okay. So I'm going to explain black holes to you in 5 minutes, no problem. So a black hole is some place where you have lots of dense matter, where light cannot escape. And Hawking's great result was that the black holes have a temperature and an entropy. And this is Hawking's famous formula for the entropy of a black hole in terms of constants of nature and the area of the black hole. And one simple way we understand this is that there's quantum fluctuations of space-time and any matter fields you have. And so there's some entanglement on the surface of a black hole. Now, if you're an observer outside the black hole, you can only see the entangled pair that's outside, not the one that's inside. And so to you, you don't even see the entanglement. You're just seeing this random qubit. And randomness is entropy. And the number of random qubits you see is proportional to the area, and therefore you understand Hawking's formula. Okay. Anyway, so what we know today that this picture is a bit too simple. This is perhaps a better picture where you have very complex entanglement without any quasi-particles near the surface of a black hole, like in the SYK model. And one reason why you might think this is the case is because this Planckian time also appears in black hole physics. It's been known for a long time. If you have two black holes merging, then they'll eventually become a single black hole, which is a sphere. And you can ask, what is the ring down time, or how long does it take to just, at the very end, become a sphere? That ring down time turns out to be, again, this Planckian time, suggesting that, okay, there's some very universal Planckian dynamics for black holes when expressed in terms of the Hawking temperature. So today, this is now much more than just an analogy, thanks to the work of many brilliant string theorists that we have summarized in this article. So what we know is that, in fact, if you take the low energy limit of two different models, take the low energy limit of the SYK model, it has a certain low energy theory. That theory is the same as the theory of Maxwell and Einstein with quantum mechanics. If you make the approximation that the only thing that matters is the radial direction. So there's this two-dimensional space-time involving the radial direction and time. And the theory of Einstein-Maxwell theory, quantum theory at low energies becomes the same as the low energy theory of the SYK model. And this is known, very precisely. And the reason you can approximate only the radial direction is the reason I have this caveat, net charge, for charged black holes or rotating black holes. That's true, is not true for neutral black holes. Anyway, so this maybe just seem like a fun analogy, but it has led to new results on the density of states of black holes, the density of many-body states, which were different from what people thought earlier from string theory. So this is the, Hawking result. This is the Hawking entropy, and Boltzmann told us the density of states is the exponential of the entropy. So that's it. But it wasn't known what the energy dependence of this is. This is the overall prefactor. What we know now is that there's this cinch square root of energy dependence, which was originally obtained in the SYK model and applies also to any charged or rotating black hole in the low energy limit. Okay, all right, so finally, to close the circle, what about the strange metal? So, this wasn't the plan in 92 when we were thinking about this. I didn't even know what a black hole was at that time. But slowly we realized that there were connections. What about the strange metal, which we were originally trying to solve? I don't think we're completely there yet, depending on the reaction of my friends to our recent work. But I think we're almost there. So we're going to think about this phase transition from the pseudo gap and the Fermi liquid. So here's a picture of it. This is our picture of FL star. This is a picture of FL. And I mentioned briefly that described by a condensation of a Higgs field. So if you're going to understand this transition, we have to also understand this dynamics of this Higgs field. So what you have to do is actually extend the SYK model, which I wrote down, which is interacting electrons, to a model of interacting fermions and bosons, boson being the Higgs field. And this particular model, that people are calling the Yukawa SYK model, has just free fermions and a bunch of harmonic oscillators representing the bosons, but a Yukawa coupling between the fermions and the boson, which is random function. And so you can solve this model, and it has essentially the same properties as SYK. And now you can go to a more realistic model of the FL star FL transition, where you have a Fermi surface of the electrons, and then you have also some spin-ons, and then you have this spatially random Yukawa coupling between them. So this is what we've been doing for the last 5 years, trying to understand this theory using what we know about the solvable models. And there's a lot of data on optical conductivity and so on that we can understand. All right, so let me summarize and conclude the talk. That was quick, but hopefully you were with me till the very end. All right, so this is my picture of the phases of the metallic phases as you increase doping of the cuprates. Here's the antiferromagnetic metal, where you still have this antiferromagnetism there. And here you have this spin liquid with these green objects floating around, carrying charge and spin together. And then finally, you have the good old Fermi liquid of Luttinger. And my first example of many-fermion entanglement was this. And the second example was the phase transition between them, which was inspired by the SYK model. And so the SYK model, here's another fanciful picture of it. It describes multi-particle entanglement resulting in loss of identity of the particles. And its extensions seem to explain some strange electrical properties of IBCO. And its dual set of variables, it's taught us more about the entanglement across the horizon of charged black holes anyway. Thank you very much.
I have a question about this analogy with black holes.
Yes.
So according to Hawking, the black holes will evaporate after a long time.
That's a much longer times.
Yeah. Does that happen here?
Well, I mean, not in the limit that I've described. So in this, if you take a very low energy limit of a charged black hole, that's essentially a stable black hole. You have to take the full 3+1 dimensional space-time to see the evaporation. Although people have been talking about some of that. Certainly the SYK model itself will not describe the evaporation. But that's assumed to be a much, much slower process. It's, you know, on any observable time scale, it's in thermal equilibrium at temperature T. Yeah.
So in your model where you have essentially the spin-on, hole-on bound together as dimers.
Let me say one more thing. What people have studied a lot, there's been a huge amount of work on this, where people take two SYK models weakly coupled to each other, and they see the energy go from one to the other, and that's what people have been using to understand evaporation. Sorry.
The reason I'm asking because nobody has seen these evaporations in universe, so maybe.
Of course not. Nobody's even seen the radiation, Hawking radiation. So, yeah.
Yeah. So in that model that you had dimers, a sort of RVB state, but with these bound dimers.
Exactly.
I'm wondering about, spin susceptibility and, or night shift measurements, if those can be made to agree, or if those, because, that's another way to sort of get at the density. Maybe not quite perfect quantum oscillations, but it's
right. Yeah, no, we've been thinking a lot about that, of course. So point number one is that this picture is a toy picture. Okay, I'm not saying this is the actual wave function. This is a wave function that helps us understand something like the Fermi surface size. It won't help you understand anything else. So you need an actual theory of the spin liquid, which we think the correct theory from a lot of numerical work anyway, is a theory with massless Dirac spin-ons. And the Fermi surface, of course, what the wave function of the quasi-particles, we have some idea from this ancilla layer model. Yeah, so the night shift, well, it will give you a pseudo gap because the Fermi surface size is very small. And the dominant spin susceptibility, at least in zero frequency, will be dominated by the Fermi surface. But if you look at this S of Q and omega at higher frequencies, where they do see these broad continua, that we think comes from the spin-on. So these bonds can break, just like in a spin liquid, and that gives you a spin-on continuum. So an unsolved problem in a realistic model is what does a spin-on continuum look like in the presence of these green objects? We have a recent paper on that in some simple mean field theory, but I'm not happy with the results yet.
So can I follow up on this? Does that mean the continuum's line shape are renormalized by the presence of these bond states, or
yes,
it's going to be the details of the continuum line?
Yeah. So this is, let's see. This is what, that's the problem I'd like to solve. We don't know how to do it yet. It's difficult. But, I would say we at least have a starting point which has the potential of this big continuum. If you look at the papers that I've written and talked about the continuum, they say, oh, these are paramagnons. There isn't even a Fermi surface, so how are you going to get a paramagnon? That doesn't make sense to me. Maybe in the overdoped side is a paramagnon. So here, at least we have a candidate excitation. We just don't know how to compute very well.
Other questions?
There's one over there.
Whenever I see like people talk about the SYK model, like a lot of the time they're working with the random couplings coming from a Gaussian distribution. Is there any interesting situation where you would look at something else?
The answer doesn't depend on the Gaussian. Okay. It's most important is the independence. As long as the independent random variables.
Right. Yeah.
Well, usually people take the same distribution. It doesn't depend on the distribution, at least in the large n limit. People have also looked at diluted SYK model with certain bonds that are exactly zero. Some fraction are exactly zero and the others are not. And that has essentially the same properties. So it's kind of like a central limit theorem, but in fact, it's central limit theorem on steroids because the number of states is 2 to the n. Yeah.
Do you see again why you believe the transition between FL and FL star is described by the Yukawa SYK model?
Yeah, that was very great. Okay, I can say a bit more about it. Actually, probably not. Yeah, so that's where the ancilla layer theory comes in. Roughly speaking, we have to have a band of spin-ons, which hybridizes with the band of electrons to make the small Fermi surface. And the hybridization between the electrons and the spin-on band is the Higgs field. So when the hybridization turns off, you get the large Fermi surface. When they hybridize, you get the small Fermi surface. So that's the mean field theory. But now we have to put in disorder, we have to put in fluctuations and so on. And that, we do by solving this field theory in some SYK-like self-consistent approximation. There's also some very beautiful quantum Monte Carlo simulations of such models by Avishkar Patel, which shows very similar results.
I'm very curious about your slides on SYK, the density of states.
Yes.
The most recent term coming from 2022 about something 394 or
Oh, that, yeah. Thank you. I went through quickly, but okay, good. Everyone was awake. Yeah, okay, 347 over 9, this thing. Right, so this is obtained by Elusive Murthy and Turiachi. And this comes from, this is where the actual particle content, it's really the property of gravity. This term would be different. There's some power of n that appears here. It's different for the SYK model. You just get 1 or something. You don't get this strange number. This is coming from the Fermi determinant of the gravitons and the photons and the neutrinos and so on. So the point is that, it's not to say that the universe is actually made up of SYK models. No, it is a standard model, and the full theory probably is string theory or something like that. The point is that is the idea of universality. So Hawking himself already, this result of Hawking is universal. Any black hole, no matter what it's made up of, has the same factor up front. What we learned now is that any black hole, no matter what it's made up of, also has this cinch factor. This is new. So these two factors are universal. This is not. And there are corrections which are probably not universal either. Maybe there's something else that's universal. I don't know. But yeah, so there's a certain universal sector, the so-called Schwartzian sector at low energies, which is present in any black hole or any theory with an emergent SL2R symmetry gives you this cinch factor.
Thank you. Questions?
One quick question. So can you say anything about the information paradox and how it relates to this?
I can't, but others have. So people have been computing the so-called page curve. Especially there's something called the island formula, which is an extension of the Ryutake-Nagi formula for evaporation of a black hole. So the page curve says that the entropy of the radiation should fall eventually, because you started with a pure state. How can the entropy keep increasing? And so there's this formula, the island formula, which I guess Pennington and various other people came up with, which claims to reproduce the page curve where the entropy goes back to 0. But it's more of it's a formula that's based upon no exact calculation, some heuristics of quantum gravity. Anyway, but you could take a model of evaporating black holes made up of SYK model coupled to some environment. And there you can explicitly do the calculation. So the Pennington formula was first tested by explicit computation on SYK type models.
Great. Okay. If there are no more questions, let's thank Suvir again for his. Next, we will have student Q&A, so students don't leave yet. I think the chair is Nelly. Could you come up?